All right, so this video, we're going to solve the following system of differential equations given up here in matrix form. And this problem is asking us to find the eigenvalues, the eigenvectors, and then use those to find the general solution in vector form, and then sketch several solutions in the phase plane. The first step in this would be to find the general solutions, and that's going to require us to figure out what the eigenvalues are for the corresponding matrix of coefficients in our system of differential equations. Okay, so the first step again is going to be to find the eigenvalues for the corresponding matrix of coefficients. And to do that, we find the characteristic equation, which is going to equal the determinant of the matrix when I subtract lambdas from the diagonal. So I'm going to get 1 minus lambda times 5 minus lambda, all minus 12. We set that equal to 0, and we solve for lambda in order to figure out what the lambda eigenvalues are. So in this case, this could be factored into lambda minus 7 times lambda plus 1. So therefore, we have two eigenvalues, lambda equals 7, and lambda is equal to minus 1. Okay, and so at this point, if I wanted to describe the general solutions, then I don't need to find the eigenvectors, right? I know that x is going to look like c1e to the 7t plus c2e to the minus t. Y is going to be some constant a e to the 7t plus b e to the minus t, and then you could plug those two suggested solutions into a differential equation and find the link between the arbitrary coefficients in the solutions for x and y. So we've already found general solutions, but now I want to show how we could use eigenvectors to express those solutions. So the next step then would be, for each of these eigenvalues, we need to find the corresponding eigenvector. So let's start with the eigenvalue of 7. So if lambda is equal to 7, then we would want to consider the matrix that I get when I subtract 7 from the diagonal entries. So I've got 1 minus 7, 3, 4, and 5 minus 7. So for each of the diagonal entries, I subtract my eigenvalue. So that would give me a matrix which would be minus 6, 3, 4, and minus 2. And now what I want to figure out is what's a vector AB, so that when I multiply this matrix by that vector, I wind up with 0 vector on the right side. So that gives me a system of two equations. I've got minus 6a plus 3b is equal to 0. And then I've got 4a minus 2b is equal to 0. And notice these two equations are redundant. They're basically the same. They're just a constant multiple of each other. So I don't need to solve this system simultaneously. I basically just have one equation 2 times over. So for example, solving the top equation for b, we can see that as long as b is equal to 2a, that's going to solve both of these equations. So for example, if I set a to be 1 and therefore b is equal to 2, that would be one eigenvector for the eigenvalue of 7. So we've got our first eigenvector for our first eigenvalue. And now we need to repeat this and do the same for the other eigenvalue, which in this example was lambda is equal to minus 1. So I'm going to start with subtracting minus 1 from each diagonal entry of the matrix. So I would have a 1 minus a minus 1, which would give me the first entry here would be 2. Then the 3 we don't do anything to, the 4 we don't do anything to, and then I take 5 minus a minus 1, which gives me 6. So now I want to see what are the conditions on this vector AB, so that when we take the product on the left, we get the 0 vector on the right. So I got a resulting system then of 2a plus 3b is equal to 0, and then 4a plus 6b is equal to 0. And again, these are redundant equations. The bottom equation is just 2 times the top equation. So solving the top equation would give me that as long as b is minus 2/3 a, that's going to satisfy this system of equations. So to give one possible eigenvector, if I set a equals 1, then we've got b is minus 2/3, and that would give me an eigenvector for the eigenvalue of minus 1. And so now we ran out of space, but we've got our eigenvalues and eigenvectors, so now we can use this to express the solution in vector form and then come up with a sketch for the phase plane. So I'm going to do that on the next slide.